Hello. Talking about vibrational spectroscopy, H psi equals E psi, that's where we always start. So we've got the Hamiltonian, which you know is got the extra potential associated with the harmonic oscillator. We get an energy, V plus 1/2, HV0, where this is a fundamental frequency dependent on the quantum wave number for vibrational modes or vibrational states. And then we have the frequency. Now notice I've got, so normally you would see this as omega is equal to square root kf over mu. Mu is your reduced mass. But here I've got V0, which is 2 pi. V0 is equal to omega. Okay? So, selection rules. How do we know if a possible transition can occur between 0 and 1, 1 and 2, 3 and 4? Well, we take the transition dipole moment operator, and this, if this equals 0, no transition. If it doesn't equal 0, transition. Okay, so because of that, we know that delta V has to equal plus or minus 1. That V comes from which wave functions satisfy the Schrodinger equation, and it gives us these V values here, the quantum numbers. Again, so it's the transition dipole moment. So here, that transition dipole moment, if I have a dipole, say, and let's draw it like that way. And so as it's oscillating, you're changing the distance here, so you're changing the magnitude of your dipole moment. So as this is oscillating back and forth, it gets longer and shorter and longer and shorter. You have a changing dipole moment. It's that fluctuation that overlaps with the oscillation of the electric field of the incident photon. Say that 3 times fast. Okay, and Atkins has some great pictures of what the molecule might look like upon overlap of the electronic dipole. But that, again, electric dipole moment operator. Okay, now, so we know delta V is equal to plus or minus 1. So if I take this condition, put it into my energy of the different vibrational mode or vibrational states, I then know that EV plus 1 minus EV. So if I go from V equals 0 to V equals 1, the energy here is V equals 0, and then here is EV equals 1. Well, then that's always going to be 1 larger. So that means that this is V plus 1 minus EV. Okay, I think you're going to do one of those in your homework. If I still gave you that homework problem, I can't quite remember. But that's how you do that. So then you just put V plus 1 into this equation. So you get V plus 1 plus a half H bar omega, H bar V0 minus V plus 1 half H bar V0. Okay, everyone following the technique? And then from there I get HV0, and I'm going to say that that is equal to HC. Here is my wave number conversion. I cleaned the board so it's squeaking. You probably can't hear it because the microphone's here, but it's very distracting. So it goes it's the squeaky marker. Anyway, so I want to get into wave numbers. Wave numbers is a very important unit. You'll use wave numbers throughout the spectroscopy section. But that's why we've got all these speed of light constants floating about. Okay, so the transitions that are allowed from here, V equals 0 to V equals 1, are going to have, when it relaxes back down, it's going to give off a photon, and that photon is going to be in the, oh my gosh, I'm losing my mind, IR regime, same as that's absorbed. Okay, but how do you get from this approach to, so here's some wave number, this is intensity. So say you have that IR spectrum. So how do you get from this picture to this picture? And you do that through the vibrational term symbols, okay? So G, V equals, actually it would be that, V plus 1/2, where the wave number is 1 over 2 pi c square root kf over m effective. Okay. So this, compare now your term symbol to your energy. So you've got the wave number here, V plus 1/2 wave number, V plus 1/2, well, H bar V0. So what you're doing is you're taking into account the wave number transition, and then V0 is 1 over 2 pi c. So there's your conversion to the speed of light, or conversion to wave number from frequency, and then there's your frequency value of 1 over 2 pi kf over mu. Okay. So these are the these are the energies in terms of wave numbers for these transitions. Okay. So when you see in your HCl-DCl plot, you're going to have each of these corresponds to a rotational transition, but the whole thing is going to refer to, so that right there in the center is going to refer to your vibrational transition. Okay. One thing I want to make clear about the size or the difference between these vibrational states for the harmonic oscillator model is that they are all the same magnitude. So if I had the transition for 1 from 0, the transition from 2 to 1, the transition from 3 to 2. So if you go from 0 to 1, 1 to 2, 2 to 3, all of those spacings would be about the same. Okay. And so you can't tell a difference if you're going from 0 to 1, 1 to 2, 2 to 3, because they're all about the same magnitude, such that if you saw all the frequencies would have a really strong peak because all of the transitions are all at that same frequency. Okay. Whereas for rotational, because each rotational is different, you have this spreading out of the frequencies that you actually see the different bands corresponding to specifically the J2 to J3 or the J3 to J2. They're very different. Here, not the same thing. Okay, so this is where rotational and vibrational are very different. Okay, until they're not. And that's when we get into anharmonicity. So this is all harmonic oscillator. So when you're applying your HCl-DCl, you're going to assume harmonic for the first round. Go team. Okay, I'm going to pause and erase. Harmonic. Okay, so now we've got the anharmonic model. So here we've got the harmonic model potential. So actually, so harmonic model, what is it? You're taking into account the fact that you don't have equal masses on a spring. So harmonic oscillation, when you've got H2, say, homonuclear diatomic, harmonic model works beautifully. So the anharmonic comes from the Morse potential, which would be a different potential energy. So the harmonic potential energy goes into the Hamiltonian. When you have a different potential energy incorporating anharmonicity, you use the Morse potential in the Hamiltonian, yielding a different wave function, yielding a different energy. Okay, and that energy matches experiment much better for diatomics that are not homonuclear, so heteronuclear diatomics. All right, so let's do a comparison between the harmonic and the Morse. So here we've got the vibrational modes so there's your vibrational term symbol, or vibrational term, and you get evenly spaced energy levels. and delta E of the vibration is equal to H nu 0, which is equal to H C V0, and then your delta G is equal to V0. Okay, so this means that the spacing between each one of these is going to be V0. That. And that's the fundamental frequency that you see when you're looking at IR spectra. Okay, the Morse potential, however, takes into account the fact that if you have, let me see if I can find a black marker. Yay, yay. Okay, so anharmonicity is going to be the same. So by the way, this is equilibrium distance. It's going to look something like this. Okay, it's taking into account dissociation such that when you get far enough away, you're going to break your molecule. All right, and so initially, notice how my black line overlaps my green line fairly well. Okay, that's because harmonic oscillation, the harmonic model, works pretty well for anharmonic transitions in the lower energy states. But as you get higher, so this is the V equals 0, V equals 1, V equals 2, V equals 3, so on, until you get to dissociation energy. And I'll explain what that is in a second. Okay, so the spacings get smaller and smaller and smaller as you go up, much like with the rotational spectra, or rotational transitions. And what happens is the fact that the difference between each of these as you get smaller and smaller, the rate at which you get smaller and smaller, gives you information about the extent of anharmonicity of your molecule. Go team. Okay. So what the Morse potential is, or what it yields after adding that potential into the Hamiltonian, operating on it, getting an energy. So G equals V plus 1/2. So it's the same thing, minus, now you're going to lose a little bit. That should be a half, by the way. I'll write this down here. So these are the same. Minus now the frequency. Actually, I don't know why I have the fundamental frequency here. I don't think it's actually supposed to be here because the values are going to get smaller. So that fundamental frequency loses its meaning when it comes to anharmonicity. Okay, so I've got the same term there, but now I'm losing a little bit. So every one of these is going to be smaller and smaller because this is going to get bigger and bigger. Okay, and so this, that's a fancy X, it's a chi. Here we go. Is equal to, this is called the Anharmonicity Constant. That is equal to A squared H bar squared over 2m effective V0, which equals the over 4 dE. There we go. So there's your frequency. This is your dissociation energy, which, did I have that right? Yeah. Yes. So is your dissociation energy of your potential well. Cool. And I'll explain what that is in a second. So you have now effective mass dependent constant, and actually A is, what is A? Okay. Oh, so A is M of, oh, well, I've just solved for A in terms of X. So A comes from the Morse potential. where you've got, so here's the actual Morse potential, dE 1 minus e to the minus ax squared, where x equals r minus r sub e. So x is going to be, oops, sorry, you can't see it. X is going to be the displacement of r from your equilibrium distance. And then a equals the effective mass V0 squared over 2hc dE. So it's taking into account the dissociation energy, the frequency, and then the effective mass. So you can see how this, if you plug this in, this then reduces down to V over, wave number 4dE. Okay, complicate. Oh, sorry. Okay. So you're going to be applying, so the Morse potential takes into account the dissociation, and you've got these additional terms now. And notice that you're taking your original model, your harmonic oscillator, and you're fixing it a little bit. This is how most of science works. If we have a theory of everything, then we don't have to do this. But we start with what we know works, and we correct it a little bit. And that correction is, we know that the spacings get smaller, so we need to subtract off some stuff. Cool? Okay, I'm going to erase. And then actually, I think the next one, I'm going to break this video up into two. Go team. The next one, I'm going to talk about dissociation energy. Bye.